So I've already drawn an xy coordinate plane here. The horizontal axis is x, the vertical is y, and I also sketched in 3 circles. They're a little lopsided, but they're supposed to be circles. Okay. So our rectangular coordinates are x, y. Basically, how we normally represent a point. Our ordered pair where x is horizontal, so left or right from the center origin, right? So negative or positive, and y is up or down. So rectangular coordinates are x and y. And I'm actually not really sure why they're called rectangular coordinates. The way I think of them is more just that we have like this grid going on between x and y, right? It's like 2-dimensional, and it makes rectangles, right? Or a square if x equals y. But you can kind of picture whatever point you have. If you draw straight up to the x-axis and over to the y-axis, that tells you your coordinates, and it also makes this little rectangle. So at least that's how I've always explained it to myself. But those are called rectangular coordinates. So there's another coordinate system called polar coordinates where we think of everything in terms of circles. So it's in terms of our radius, the radius of the circle that we are on, and the angle that that makes with the positive x direction, right? So from here, this being 0, and then you go all the way around to 360 degrees or 2 pi radians, and then you can keep circling, right? It's cyclical. So, and you can also go negative too. So, we've kind of already touched on that with the unit circle, and the unit circle is a special case. The way that we've worked with it is a special case of polar coordinates. So the polar coordinates have to do with your radius r and the angle theta that you make with this positive x. Okay, and so I've drawn 3 circles here. They are supposed to be, 1 unit apart. So if this first circle has a radius of 1, and this next circle has a radius of 2, meaning this distance should equal this distance, which equals this distance. Okay. Then this first circle, the smallest circle with a radius of 1, is actually our unit circle. It is centered at the origin 0, 0, and has a radius of 1, meaning by the definition of a circle which has a center and all the points on a circle are equidistant to your center. So if the radius is 1, it means every point on this first circle is a distance of 1 to the 0, 0, the origin where x and y meet. Same thing for 2. So every point here is a distance of 2 to the center. And same with 3. Okay. So it's all kind of about the radius, the radii. So if I had a point, let's say I put a point right, I'll just do this let's say I put a point right here. Okay, that is going to form an angle if I draw from that point to the origin. That is going to form an angle to this positive x direction, and that's theta. And we've already kind of talked about theta going from 0 to 2 pi, and that sweeping out my unit circle, right? However, in this this radius of 2 circle, it's actually a distance of 2 from the origin. So r is 2, and so that's going to look like 2 comma, and then whatever this angle is, and we can calculate that if we know our xy coordinates, if we actually know the horizontal and vertical coordinates, or we can just use a protractor to measure that angle, but that might not be super precise, right? Depends on what the values are. But that's the idea. So instead of thinking x and then y, we are now thinking radius and angle. And that's it. So we can actually convert between the two. And we're going to kind of do a little derivation now to see how you do that. But before I get into that, I wanted to mention that just like just how x and y can be negative and positive, depending if you're left or right or up and down, r can actually be negative. So it's possible to have a negative r, even if that doesn't make sense to have a negative radius. But the negative actually has to do with the direction. So, for instance, if I have, let's see, if I have negative 2 comma 30 degrees, and your theta can be in degrees or radians, you would draw where 2 comma 30 degrees is, which is on your second circle, so 2, and then the angle that's created that makes 30 degrees, so it looks something like right here, because 45 degrees would be your halfway point, right? Because this is 0, this is 90 degrees, this is 180 degrees, this is 270, and then you're back at 360. So 0 degrees and 360 degrees are the same, right? So 45 would be halfway between 0 and 90, and so 30 would be a little bit less than that, right? So like right here. So this point right here would be my 2, so positive 2 comma 30 degrees. But then the negative 2 just means, so I'll just go ahead and draw that right there. The negative 2 just means I take that and go the opposite direction, so it's actually here. Oops. Yikes. I actually don't mean Oops. I actually didn't mean to go that far. If I only had a radius of 2 in the first place, if I'm going the opposite direction, I am still on that second circle, so I didn't mean to go to the third. But that's a fun opportunity. It's okay. Some liquid sounds here for my whiteout, but let's just white this out. Ta-da! Okay, but notice that is actually equivalent to having a positive r of 2, so not negative 2, but where the angle is this whole angle here, it's the 30 plus another 180, so 210. So that's the same as 2 comma 180 plus that 30, so 210, right? So those two are equivalent. So just being sure which way is your positive, you can just graph positive and then go the opposite direction for your negative r. Okay. Anyways, we'll get more practice with that, but I wanted to kind of make this leap from x comma y to r comma theta, and this is really just based on the proof that we did for the unit circle, but we are going to generalize it for any r. And also note that your r, this is just the concept, but just how x and y coordinates are not always integers, right? You can have, 1.2 are going to do is take a general point. Let's say we have here, this point looks nice, so I'm just going to stick with that one. And let's say we have coordinates x comma y. So this has rectangular coordinates x. Oopsies, I don't think you're going to be able to see that, so let me try and write that. Okay, so we have x comma y. Okay, can you see that? X comma y. So that means for rectangular coordinates, I'm going to draw this vertically straight down. And it kind of looks like it'll hit the 1 in this case, but it doesn't really matter, okay? We're not actually, we're trying to generalize, and this is just how my picture turned out, but it doesn't have to be 1, okay? So basically, you see that there is a rectangle formed here. If I draw vertically down and this way, right? So, let's see, we have this is the triangle I am focusing on. Okay, so this is R. The diagonal here is R because that is the radius of, in this case it's on 2, so we know that, but let's generalize for any R. Okay, and we have our angle theta. So basically we are looking at a right triangle, and I'm just gonna pick that up and move it so that we can see this clear picture. And it does not matter like what my actual R and theta is. That's why I'm trying to generalize this. So our right triangle might look, you know, like this. It does not matter, right? Because I can do the same triangle for, say, this point and just draw straight down, right? So that is also perpendicular. So basically, the hypotenuse is always going to be R. My angle is going to be theta based on my polar coordinates, and my height, given that these are my x comma y coordinate planes, or the rectangular coordinates, my height is going to be y, and my going horizontally is going to be x and y. You see that? So no matter what the actual coordinates are, whatever those values are, it's just going to be x horizontally and then y vertically. Okay, so, and then my angle is still my theta. So I'm just focusing on this first quadrant, from 0 to 90 degrees first, because then we can do the same logic and kind of reflect into each of the other 3 quadrants, okay? So now the question is, how are R, theta, x, and y related? So using either rectangle here, I can first use the Pythagorean theorem, because I have x and y, and then I have R being the hypotenuse, and it's a right triangle. So we know that x squared plus y squared equals R squared. Okay, nice. So that's one equation that we can use. And then we kind of need to remember SOHCAHTOA, and link that video in the info box. But this is sine is opposite of hypotenuse, cosine is adjacent of hypotenuse, and tangent is opposite over adjacent. But we really only need sine and cosine for right now. So if we look at, let's start with cosine of theta, right? So cos of my angle, so cosine of theta in a right triangle is the length of the adjacent side, so that's x over the hypotenuse. That's what the ka part tells me. So you have x over r. That means that if I just move this r over to this side by multiplying, right, x divided by r, so if I move it, I multiply. Or you can think of it as multiplying by r on both sides of the equal sign. I get x equals r cosine theta. And that is my equation number 2. So this is how I get my rectangular coordinate, my x rectangular coordinate, in terms of r and theta. I do r times cosine of theta. And so you can imagine sine y is similar, but with sine, because sine theta is opposite over hypotenuse. So placing where my theta is, which is just this one, the length of the side that is opposite of theta is y, and the hypotenuse is r. So y over r. And again, if I move the r over, I get y equals r sine theta. So that's my other equation. So if you remember, I'm not sure if this was just kind of in the middle of one of my videos, but if you have the unit circle case, r equals 1. So when you have the unit circle, you can actually, that's like the first time we're really studying cosine and sine in the first place. The point of bringing in sine and cosine as trig functions is to kind of give us a way to just read straight off of our unit circle, so that x is my cosine, like that x coordinate is my cosine of theta, and the y is sine of theta when r equals 1. But here we go. These are our 3 things to know. So we can calculate our r based on x and y. So if we go from rectangular to polar, polar to rectangular, we will use this. And going the other way, if we are given, this is more from polar to rectangular, right? So if we are given r and theta, we can just plug in r cosine theta to get x and r sine theta to get y, and that's my rectangular thing, right? That's my rectangular coordinate. Going the other way, just to mention it here, we know that tangent of theta equals the opposite over adjacent, so y over x. So going the other way, we can actually use inverse tangent and plug into this to get r and theta. So there we go, just to kind of finish off what we're doing. So these two for going from polar to rectangular, these two from going rectangular to polar. And the other thing we have to consider is, like we said, whether we are picking r to be positive or negative, because that will change our corresponding angle. But even from this formula, you can see, like, even if we get x squared plus y squared equals, I don't know, let's say it's 100 for whatever reason, then r is equal to plus or minus the square root of 100, so 10. So you can get plus or minus 10 because r can be positive or negative. But depending on that, you can adjust where your theta is. Okay, so which quadrant it's in. Okay, so we kind of need to do a little bit extra work there. So we can actually get polar coordinates that are equivalent changing the r, so the sign of r, like the plus, positive or negative sign is what I mean, not S-I-G-N of r, and changing the angles to get equivalent points. Okay, so we will do actual practice with this, but I wanted to do this little derivation. I think this turned out to be kind of like a sleepy video, but maybe it's just relaxing to have in the background. At least I hope so. And I hope that it gives you a little bit of intuition about where these formulas come from. And so for our derivation videos, they do get a little bit longer. So of course we can always come back to these two equations and make like shorter, just let's memorize together videos. But I hope that this was interesting and helpful. You can try drawing out these triangles yourself, but the most important thing is to label your x comma y, and then realize that the vertical part, if I made a right triangle, and you know that it's perpendicular because the y axis is perpendicular to the x-axis, but knowing that it's a right triangle, the vertical leg is y and the horizontal leg is x, and that's because of the way we define x comma y, right? It's horizontal then vertical. And then we know that the hypotenuse is going to be my r and the angle formed is theta, and from there we use our SOHCAHTOA and our Pythagorean theorem, and that's how you get the general conversions. But like I said, we will practice. So just let that sink in a little bit, and I will see you soon. And let me know if you happen to be studying this stuff.